So in the beginning of Fourier analysis, what did we say? So in Fourier analysis, we said that we are going to represent any signal using some basis functions, and we said the basis functions that we are going to choose are phasors because they are orthogonal and they are bounded. So the questions that we had at that point of time, what should be the choice of indices, basically what should be the choice of the frequencies, and how to find the inner product to compute the coefficients. Those are the two questions that we had. Now the first choice we made was we will make this set of frequencies discrete by choosing the harmonics. Now what if in the very beginning we did not make that choice but made the choice to have all the frequencies to be continuous there itself. So if we had made the choice there itself that all the frequencies of the phasors to be continuous, then we had frequencies all from minus infinity to plus infinity. In that case, the representation at that point of time itself would have changed to have the integral, because we cannot now write it as summation. You cannot now write it as something like this because it is not discrete. This value is from minus infinity to plus infinity, any arbitrary value can exist. So you cannot use the summation, you have to use the integral, and for each omega you have a corresponding coefficient, right. So this is still adding up multiple phasors with different magnitude and then just putting everything together, you get this signal. So we are still saying we will represent the signal in terms of our bases, which are orthogonal phasors, and these are the coefficients, So this is our original Fourier analysis representation. Okay. Now under this representation, how do we compute this coefficient? So if we know how to compute this coefficient, then we are done, right? So this is all we wanted. So we have already made the choice, that is, we will use all the possible frequencies from minus infinity to infinity. So the choice is done. So the next question is how to find the projection or the inner product, how to find this coefficient basically. Now given that this is true, how did we find the coefficient? All we did was, remember, just x transpose z, you compute that, on the other side you are supposed to get this coefficient and x transpose x, right. So do the same thing here, compute this projection, and in this projection, of course, because this is aperiodic, you have to have this integral from minus infinity to plus infinity. And what do you do if you compute that? In that case, then we'll have minus infinity to infinity a nu e power j omega t dv. This is our z of t. So I'm just going to expand this integral here. So this is z of t. Okay. So this is multiplied with e power j omega t dt, and then we compute another integral here. This is from minus infinity to infinity. So this is the expression that we have on the left hand side. So we can rearrange this. Okay, we can say that, okay, I'm going to swap the order of integral. I'm going to bring this a b outside and keep this j omega t and e power minus j omega t inside, and going to integrate this with respect to dt first. So in other words, we are going to integrate e power nu minus omega t dt. So this integration is quite complicated. So take it from me that this is equal to 2 pi delta of nu minus omega. Okay. So to evaluate this is quite complicated. It's a long integration. I'm not going to prove it. You can do this as an exercise if you want, but it's a long derivation. So let us assume that this is true. So if this is true, what does it say first? It says that the evaluation of this integral is 0 for all values of nu and omega such that nu is not equal to omega. This makes sense. Why does it make sense? Because what is this integration after all? This integration is e power j omega t into e power. So this is the inner product of a phasor with frequency nu, another phasor which has a frequency omega. So we know that because they are orthogonal, only when these two frequencies are equal to 0, this integration will be non-zero, otherwise it will always be 0. So that's the definition of orthogonality and orthogonal phases, right? So this has to be 0 for all nu and omega which are not equal. When they are equal, because you are integrating from minus infinity to infinity, you are supposed to get an infinite number. And we know a way of quantifying these things which go to a very large value for one particular value of the input variable, and that is the Dirac Delta function. So with the Dirac Delta function, we will say that this entire integral goes to infinity at only one point. In all other points it is 0, okay, and it goes to infinity such that this area is going to be 2 pi, okay. So putting that back into this integral, this is what you get. So once again, from the properties of Dirac Delta, we know that if we are going to integrate some a of t delta of t minus t naught dt, we know that this is equal to a of t naught, right. So that's exactly what we have here. So instead of t we have nu, and instead of t naught we have omega. So which means we have a of omega. So this entire integration is now going to give us a of omega times 2 pi. Okay, we just use the property of the integration. So what this tells us is the inner product of the signal with the phasor over the entire time duration. This is an aperiodic signal, right. So for that is represented by this z of j times omega. We'll call this as z of j times omega, and that, because we have j times omega here, and that is equal to a times omega by 2 pi. Okay. Now substituting this back into this equation, what do we have? We have now z of omega to be inside this integral. That is, you can represent the signal z of t as z of j omega divided by 2 pi into e power j omega t d omega. All we have done is just substitute this into our first equation. Okay. So we can bring this 1 by 2 pi outside. So how do we compute z of j omega? So z of j omega comes from this equation, which is integral minus infinity to infinity z of t e power minus j omega t dt, which exactly gives us the analysis that we did here. So you take the Fourier series representation, there you let the period tend to infinity, you get exactly the same representation that we have now. So either you can choose at the beginning itself to have all frequencies in your representation, or you can have a discrete set and then extend that to a continuous set. In both the cases we get this representation. Okay. So the moment we have this representation, the next question is what happens to Parseval's theorem, right? So Parseval's theorem stated that the energy in any representation is exactly equal. So then we should have the representation here also to satisfy the property that the representation of the signal either in z of t or in z of j omega should have equal energy. Is that true? That has to be true. But how do we show that if the energy goes to infinity and so on? So once again, with Dirac Delta functions we can manage that also. We will see how is that. So we know that the squared magnitude of z of t is equal to z of t times z of t the whole star, and that is what we have here. This is z of t and this is z of t star. Okay. So this is only the z of t the whole square. So we are not integrating with respect to time now. We will just compute this integration first. So what is this integral? So this integral says this is a nu a omega. We'll have to use nu and omega because they are two different integrals, not the same. So we should not confuse the variables. So we'll have two different variables, and writing them together you have the double integral of this form. Okay. Now you can write this as e power, right. So what is this? Now we can do one integral first. So we can use whatever we did here. How did we get this Dirac delta? Because we were integrating this, right? So the computation of the energy now is equal to integral of this minus infinity to infinity dt. Now what we will do first is we will bring this integration inside and compute that integral first. So computing this integral first, we would get a new a omega star 2 pi delta of nu minus omega. So that's what we saw earlier. So we'll use that result here. So if we use that result here, what do we get? Now evaluate this integral first. So if you evaluate that integral first, then we would end up getting a new integral a omega star 2 pi d omega dv. We keep changing the order of integration so that our life becomes simpler. Evaluate this. This is 1, or basically the same result once again. So this is equal to a omega star when nu is equal to omega. In other words, you can replace this entire thing with a nu star times 2 pi. Okay, so in other words, this is 2 pi times integral a v dv. Okay, all right. Now let's simplify this even further. We know that the relationship between a nu and z of j nu is given by this expression or this expression. So we can represent this energy here by substituting this relationship into this equation. Then we get 2 pi times z of j nu mod squared divided by 2 pi the whole square times d nu. So this 2 pi gets cancelled and we get 1 by 2 pi. So the Parseval relationship still exists, and we got rid of the problem of infinity by using this Dirac delta, and then we integrated the Dirac delta out so that the area was always now finite. So essentially we went through infinity and then still got back to a finite number because of the help of Dirac delta function. So that's the power of Dirac delta function. It helps us to show that Parseval's theorem is true no matter what. So this still tells us that the energy of the signal in any representation is the same. So you get the energy here in the time domain representation, which is given by this integral, and this is equal to the energy in the Fourier domain representation or in the Fourier transform domain representation. In other words, putting everything together, given any signal x of t which is not periodic, okay, if the signal is not periodic, you can write this x of j omega, which are basically nothing but the Fourier series coefficients multiplied by 2 pi. Okay. So the Fourier transform of any signal is simply nothing but this inner product, the inner product of the given signal with the conjugate of the phasor e power j omega t. Okay. So the Fourier transform, always remember this as the inner product. So remember that you have to take the given signal and multiply that with the conjugate of the phasor and integrate to compute this inner product. Basically you are projecting the given signal onto, so project x of t onto e power j omega t. That's all you have to do to compute the Fourier transform. This is what we will call as the Fourier transform. So if you do that, then what you get is the component of x of t on the phasor e power j omega t. Basically, what is the amount of the frequency omega that is present inside x of t? That is what we will get, and that is what we will call as the Fourier transform. So, this is the Fourier transform, very important tool for all electrical engineers. Now, somebody, if they give you the Fourier transform, can you get back the original signal? Yes, of course you can get back, because after all what we are doing is we are representing the same signal in a different form, right? So, we should be able to get back the original representation, and the original representation can be gotten back by computing the inverse Fourier transform. The inverse Fourier transform is basically what? Just adding up all the phasors. So, we know the phasors are e power j omega t. All you have to do is scale the phasors accordingly. You have to adjust the magnitude of the phasors, right? You adjust the magnitude. Of course, remember we added a 2 pi extra there, correct, to the coefficients. So, you have to remove that extra 2 pi from the coefficients, and so that divide that here, okay, and you are done. Put everything together, you get the original signal back. So, this is called the inverse Fourier transform. So, this is the conventional expression for Fourier transform for any given signal x of t, which need not be periodic, and to get back the original signal, this is the inverse Fourier transform, or basically this is the expansion in terms of the phasors. The expansion of the time domain signal in terms of the phasors is denoted through the inverse Fourier transform, and the coefficients of each of the phasors is represented through the Fourier transform. Now, the Parseval's theorem tells us that the energy in the time domain is equal to the energy in the frequency domain. That is exactly what we have here, but of course, these are only inner products without the coefficient scaling 2 pi, so that we are removing here. So, remove the coefficient scaling 2 pi. So, the energy of x of t is computed through this expression, and the energy of x of j omega is computed through this expression. Basically, the energy of x of j omega is just this expression, right, over all values of omega. So, they are exactly the same except for the scaling factor of 1 by 2 pi that comes because of this relationship here, okay, alright. So, this is Fourier transform.